Hello class, so this is the lesson that I was going to teach you today, group 200, I'm sorry, 410. I'm sorry about missing the lesson. And it's about the rational function, this thing, the rational function. So let's read. We have the following definition. A rational function is a function of the form f of x equals g of x over h of x, where g and h are polynomials and h of x is different than 0, because of course this function over here cannot be 0, right? If this is to be understood as something mathematically valid. So basically, a rational function means a function that is understood as the division of two polynomials. But in particular, in this course, g and h will be restricted to be linear functions, and thus the rational functions for us will be having this shape, ax plus b, which is a linear function, right? It's a polynomial, but a linear polynomial, and over cx plus d, which is another linear function. And what are a, b, c, and d? They are any real numbers. That's it. If we notice the reciprocal function, which is this one, the one that we have been studying in the previous weeks. This is the reciprocal function, right? And we have been studying as well some of its transformations. Well, this function, guys, is nothing but a special case of the rational function, which is this one, like I said before. If we make the constants a equals 0, b equals to 1, c equals to 1, and d equals 0. If you give these particular values to these constants, guys, pause the video and you will realize that this function reduces to the reciprocal function, which is this one. So what is the conclusion here? The conclusion is that this function is nothing but a special case of this one, right? Or you might say that this function is the general case of this reciprocal function. Okay, and actually all the transformations of the reciprocal function are nothing but special cases of the more general rational function, right? For example, something like this. Give me a moment, please. Okay, so as I was saying, guys, all the transformations of the reciprocal function, let me write one of those. So for example, you have something like this. We know that this is a transformation of the reciprocal function, right? Maybe I should call it differently. Remember, you cannot use the same name for a function if you have two different functions, right? Actually, this is also a mistake, right? I'm saying that f is this, and in the same context, I'm saying that f is equal to this. This is technically incorrect. I made something wrong here. So this is a transformation of the reciprocal function, but then you can understand that this is nothing but a special case of this, right? And if you want me to prove that, just make the a equal to 0. I'm gonna write here a equals 0, b equals to 2, c equals 1, and d equals -3. If you give these particular values of the constants to this function, then you will get this particular function. Okay, so bottom line, the reciprocal function and all of its transformations are nothing but special cases of the rational function. Okay, the rational function. The rational function behavior is very similar to the reciprocal function. Here we have two rational functions, f and g, and their respective sketches. So look at the graphs, at the sketches. Well, they're not sketches, they're actually the graphs. This is the function f, rational function. As you can see, we are dividing a linear function over another linear function, and you get this, right? We have the same behavior as with the reciprocal function. We have asymptotes, right? I'm gonna try to draw them. You have this asymptote over there. You have this asymptote over here. So we have two asymptotes, vertical and horizontal. we have two branches, etc. So basically they are hyperbolas. And the same with this one, right? G is the same, right? So their behavior, the behavior of the rational function is pretty much the same as the reciprocal function. And finally, for the last slide of this lesson, let's read the following. As well as with the reciprocal function, we want to obtain the main features, and that means the asymptotes, the intercepts, and a few telling points of the rational function in order to sketch its graph. The book offers a good recipe to do this. In the book, guys, when you're in this section for the rational function, there is a page in which you have this little section, and it says sketching rational functions from the equation without the use of technology. The general equation of a rational function is this, right? And to sketch this function without the use of your calculator, you should follow these 6 steps, which is pretty much what we have been doing for the reciprocal function, which is finding the vertical asymptote. I'm going to make a comment about this in a moment. Find the horizontal asymptote, find the y-intercept, find the x-intercept, and then number 5, test values on either side of the vertical asymptote to determine whether the curve tends towards positive or negative infinity on that side. And by this number 5, guys, what they mean is basically what I'm writing in here. Like give a few telling points, right? So that you can understand how in what direction the branches are. For example, we have these two broad differences or classifications. Suppose that you have two Cartesian planes and you have these asymptotes. The same asymptotes in both of them. Okay, that's not enough to know the behavior of your function. You need to know where the branches are, because you may have this case, right? Or you may have this case. You see? So how do you find out? By testing with some values. That's how you find that out. Okay, and then number 6, draw the axis and the asymptotes and then sketch the curve. Okay, now the comment I was gonna say about these guys, about these two formulas in here, look at this formula and look at this formula. The book already gives you the formulas for the vertical asymptote and the horizontal asymptote of this rational function. Okay, if your function looks like this, exactly like this, then the vertical asymptote is automatically x equals minus d over c, and the horizontal asymptote is automatically y equals a over c. And I want to prove that to you. And we're going to use basically the same idea. Give me a moment. There you go. Okay, how do we prove this? Very, very easy. For example, let me write this function over here. I'm going to write it in f of x notation. Okay, and then let's find the vertical asymptote of this function without making reference to this formula. For vertical asymptote, it's going to be x equals some value, right? And how do I find that value? Okay, what we need to do is make the denominator equal to 0. Okay, so cx plus d equals to 0, and then we solve this equation, right? And if you solve this equation, you're gonna get cx equals minus d, and then x equals minus d over c. So this is the vertical asymptote. And why am I doing this? Why am I making the denominator equal to 0? Why is this the approach to find the vertical asymptote? Because you must remember that the vertical asymptote is that line in which the function goes to infinity, right? For example, this is the Cartesian plane. And then if this is your asymptote over here, then what's happening is this. If the x approaches this particular value, you get that the function goes to infinity in this way. Or conversely, it goes to minus infinity. So you should look for a specific value of x in the x-axis, for a specific value of x for which the function goes or explodes to positive infinity or to minus infinity, right? And how can you make that? How can you cause this function, which is all of this fraction, to go to infinity? Well, you can cause that by making this denominator equal to 0. Because if you divide whatever, any number, over 0, you cause an infinity. And what is that number of x that makes the denominator 0? It's this value. By the way, I made a mistake in here. CD minus... I made a mistake from the start, sorry. It's like this, minus d over c. So there you go. We have proven that that the vertical asymptote is this, right? There you go. Now for the horizontal asymptote, you have this function. Once again, there you go. And for the horizontal asymptote, remember what you have to do is make the x, the variable, approach infinity, and then observe whether the function approaches a specific value. A specific value, guys, a specific number. Okay, you must find a number here. And if you find it, then that number is going to be the horizontal asymptote. So how do we proceed? We proceed in this way. We write the fraction. There you go. And then I'm going to divide both the numerator and the denominator by x. And you may be thinking, well, why are you doing that? Like, sorry, what's it seems something out of the blue, right? Something without purpose. But so far, what I can tell you is this. I can do whatever I want as long as it's mathematically valid. Can I do this? Can I get away with dividing numerator and denominator by the same number? Yes, of course. It's in the same way that you can perhaps, if you have this fraction, 2/4, you can divide the 2 over 2 and the 4 over the same number, which is 2. And what do you get? You get 2 over 2, 1, 4 over 2, 2. And you know that 2/4 it's the same as 1/2. So you can always divide both numbers by the same number. It's got to be the same number, and you're doing fine. I mean, that's a mathematically valid step. So let's do that. Let me divide numerator and denominator by x, and then let me simplify this thing a little bit. So what are we having here? We have ax plus b over x. If I divide this term over x, I get a. And if I divide this term over x, I get plus b over x. You see? I'm simplifying this into this. Over, and then the same, cx over x, you get c. And then d over x, you get plus d over x. Okay, so basically I have changed this form of the function into this equivalent form. They are completely equivalent forms. And at this moment, guys, right there, when I have the function looking like this, that's when I make the x approach infinity, right? So let's do it. Let's make the x approach infinity. And this fraction, let me put that in yellow. If x approaches infinity, then this fraction will go to 0 because you're going to be dividing b over infinity, or basically b over an incredibly large number, and the whole fraction will approximate 0. And the same with this. Okay, this will go to 0 and this will go to 0 as x approaches infinity. And what remains? Well, the only thing that remains are this a and this c. You see? That's it. So what is my conclusion? As x approaches infinity, then the function, the output, approaches A over C. So therefore, I could find a specific value, which is that value that I was talking about, and therefore that will be the horizontal asymptote. It's gonna be A over C. There you go, which is the formula that you have in here. You see? So we have proven that these formulas are in fact correct, and you can use them as long as the function looks like this. There you go. Okay, guys. So basically that was the whole lesson that I was gonna teach you today. And the only thing that remains, let me go back here, is this exercise. I want you to sketch the graphs of these functions, f, g, and h, by following this recipe. Okay, do all of these things in order, and then sketch the functions for the next lesson, which is tomorrow. So thank you so much, guys, and I'm so sorry about missing class today. I got all mixed up. Thank you so much.